Good day, everyone. I will discuss to you about Borel sets. But before this one, let me have an overview about an open set in R. So we have here the definition. When can we say that a set is open in R? So it is open if and only if for every element in the set, there exists delta greater than 0 such that this set here is contained in the set O. Now let's try to have this example here. So let us have set O be the open interval from 1 to 5. So let's consider this real number line. Now, let's have the existence of delta. Take note, delta is greater than 0. So if we are to consider, we let x rather be in the element of the set. So say for example, we have here 2. So we have here, this is delta, distance from 2 to this point, and then from 2 to this point we have delta. Therefore, this point here is 2 minus delta, and here, this is 2 plus delta. So we now have here an open set. Now take note here, the open interval here from 2 minus delta to 2 plus delta is contained in the set O, the bigger set here. And if we take another element, take note for all x. This is for all x in the element. So we can take any elements here, and then we set our delta be greater than 0. So for example, we take an element here. Then delta could be smaller as long as it is greater than 0. We can take or set the interval here smaller as possible. So it is always contained in the set O. So if we get here an element of O, and then there always exists delta greater than 0, or there always exists an interval that is contained in the set O from 1 to 5. Therefore, this set here is open. Now what about if we try to consider this set from 1 to 5, this 1. So let us try to use the definition there to show that this is not open. So say for example, we have here from 1 to 5, this is closed. Take note, x is in the set. So for example, this set is F. We set this as F. So for all element x in F, there should exist delta such that this interval here is contained in the set. So if we take element here, if we set the delta, of course it is contained. Now what about if we take an element here? Take note that 5 is in the set, right? 5 is in the set. Now if we take delta, smaller, as you can see, bisag paghamyan pa na nimo siya ang interval, this interval is not contained here. Follow? So it means that this interval 5 minus delta, 5 plus delta, is not contained in F. It is not contained in F. Therefore, this set here is not open. Okay. So let's use proposition 2.25. So from proposition 2.25, it states there that there exists a smallest sigma algebra, and we denote that as script B, such that all the collection of open sets is contained in the sigma algebra script B. So this is our script U, which is the collection of all open sets in R. So these elements of script B are called Borel sets. So let's have here examples of Borel sets. So some Borel sets are all open sets, all closed sets, countable intersection of open sets, and countable union of closed sets. That is, we can let A, B be two real numbers, where A is less than B. So this open interval here is an example of Borel set. Another one here is an example of Borel set, because this is closed set, and we know that closed set is a Borel set. Then the countable intersection of open sets is a Borel set. So if we are to take the countable intersection of all of the open sets, so it is also a Borel set. Also, if we are to take the countable union of closed sets, so these are examples of Borel sets. Okay, let's have this definition. A set G is a G delta set if it is the countable intersection of open sets. That is, we can write it as in this form, where O sub I is open for each I. So take note, from the previous example, we know that countable intersection of open sets is an example of Borel set. So let's have here another example of this set, which is the countable intersection of open sets. So as you can see, G is written in this form, the countable intersection of open sets. Open interval from -1/n to 1. So in that case, we call this set as G delta set. If we can write G in this form. So another definition here is for F sigma set. So again, for countable union of closed sets is one of the examples of Borel set. So a set F is a F sigma set if it is countable, if it is the countable union of closed sets. So it means if we can write F in this form, then we can say that this set is an F sigma set, where F sub I here is closed for each I in the set of natural numbers. Okay, for example, if the set F can be written in this form, it is the countable union of closed sets. So we can say that set F is an F sigma set. Now let's have this example. First, open sets are F sigma sets. Why? Let's try to consider this example here. We will show that this open set is an F sigma set. It means we can rewrite this one as the countable union of closed sets. That is for F sigma sets, being the countable union of closed sets. So we can rewrite this as the union of this B minus 1 over n, where n is from 1 to infinity. So this countable union of closed sets is equal to the open set 1, open interval from 1 to 3. So this open interval is, of course, an F sigma set. So let us try to illustrate why this is equal to the open interval. So let's consider this the real number line. So let's have here 1, then 3. So when n is 1, we have 2. Here 3 minus 1 is 2. And when n is 2, we have 1 plus 1/2 is 1.5. So here, interval is here. 3 minus 1/2 is 2.5 here. Then when n is 3, given n is 3, so we have 1 plus 1/3 is somewhere here. It's somewhere here. Then 3 minus 1/3 is somewhere here. Now, when n is 4, so 1 plus 1/4 is 1 and 1/4. So it's somewhere here. Then it's somewhere here. Now, as you can see, this set here, the sequence of these sets here is increasing. Padulong siya sa 3. This one is padulong sa 1. Now, if we take the union, countable union of closed sets, we can have open sa 1 and then open sa 3. Now, why we do not include 1 and 3? Because as n approaches infinity, this approaches to 0, but it will not be equal to 0, right? So 1 plus greater than 0 or approaching to 0 is na lang siya open. The same thing here. That's why the countable union of closed sets here is equal to the open interval 1, 3. So, again, open set is an F sigma set. Our next example is closed sets are G delta sets. To show this, let us consider this example, the closed interval from 2 to 5. So we are going to show that this closed interval here is a G delta set. So it means we can write this one into countable intersection of open sets. To infinity. Okay, so this form is G delta set, being the countable intersection of open sets. Now let's try to illustrate this one, why this is equal to the closed interval. Now let's try to consider the real number line. We have here 2, we have 3, 4, and we have 5 here. Now when n equals 1, we have 2 minus 1 is 1. So we have here our open interval. And then 5 plus 1 is equal to 6. So when n is 1, we have the open interval from 1 to 6. And then when n is 2, we have this becomes 1/2. So 2 minus 1/2 is 1.5. So we could have smaller interval. So somewhere here. And then 5 plus 1/2 is 5.5. So somewhere here. Now as you notice, as n gets larger, so approaches infinity, the sequence of the open intervals here is decreasing. It is closer to the interval 2 to 5. So take note again, it is getting closer to 5. Take note that this could not be equal to what? 0, 1 over n. 1 over n, as n approaches infinity, this also approaches to 0, but it will not be equal to 0. So it means 2 minus a positive number, a smallest positive number, is less than 2. So it means if you're going to get the intersection, 2 is included. The same thing here. This could not be equal to 0, so 5 plus the smallest positive number. So it means if you're going to get the intersection, 5 is included. That's why this is equal to the closed interval from 2 to 5. Okay? Next. Okay. This interval here is both a G delta set and F sigma set. So this will be your problem set. You're going to show the countable intersection of open sets, which is equal to this interval, and so with the countable union of closed sets, which could be equal to this interval. So we note that the converse of 1 and 2 above is false. It means open sets are not G delta sets, and closed sets are not F sigma sets. So let's have here theorem 2.30 rather. So first, a set is an F sigma set if and only if its complement is a G delta set. So this is an if and only if statement. It means we will prove this in 2 ways. Okay? So let's have this. First, we let F is a F sigma set. And then we will show that its complement is a G delta set. So let's have this first proof. So we let F be an F sigma set. So since F is an F sigma set, so we can write F as the countable union of closed sets. So our F sub I is closed for all I. And then we will get its complement. And then we will show that the complement rather is a G delta set. It means we can rewrite its complement into its countable intersection of open sets. So let's get the complement of F. So this becomes we have this one. So F complement therefore is equal to, so by De Morgan's law, union becomes intersection, and then we have here the complement of F sub I, where I is from 1 to infinity. Now take note, F sub I is closed, so its complement is of course open for all I in set of natural numbers. Okay, now the complement of F is written as the countable intersection of open sets. It means the complement is a G delta set. So we're done proving the first way. Okay, to prove the other way, we will consider any set, and then by assumption, we will get the complement of that set, and the complement is a G delta set. Then we will show that that set is an F sigma set. So let's do this. Okay, so let's have this. We left, so for this, let, say for example F, so you can use any letter, so let F be a set. So what we're going to do, we are going to show F is F sigma set. Okay, so to show this, by assumption, we will use the assumption that the complement of this is a G delta set. So it means, here, by assumption, we have the complement of this set is equal to countable intersection of open sets. Say for example O sub I, where I is from 1 to infinity. So it means that the complement of this set is a G delta set. That is our assumption. So to get F, we will get the complement of both sides. So F complement, because F complement of the complement is equal to F. So we also get the complement of this, infinity. Okay, this one. Now take note, O sub I here is open, right? With the definition of G delta set for all I. And so the complement is, we have F here for this. So by De Morgan's law, we can say that the complement of the intersection is the union, and then we have complement of O sub I, where I is from 1 to infinity. Take note that O sub I is open, therefore its complement is closed for all I. So this now becomes the countable union of closed sets. Hence, we have shown that F is an F sigma set, being the countable union of closed sets. Okay? So we're done proving the first statement here. Now the next one is a set is G delta set if and only if its complement is an F sigma set. So this will be your problem set number 6. You're going to prove this statement rather. So we're done.